Hi everybody, I'm Skip Elshammer. Welcome to the AV Geeks lunchtime streaming show, where I was just making some uh, salad. Let's see. So many things to do today. Got some 16mm films to watch, which is what we do while I'm eating lunch. So behind me I have it on the film scanner. Let's see. What is it? Land, Use, and Misuse. Enjoy.
The sun is the primary source of all the Earth's energy. The oxygen we consume, the food we eat, the fuel we burn has all been produced by the sun's energy. This production takes place at the surface of the Earth, a surface we are rapidly changing. What happens to this desirable property when we remove its vegetation? When it rains? Equal amounts of water fall on both sections of land for the same length of time. We see that a great deal of soil has been washed away on the cleared side, very little on the covered side. These heat lamps will simulate the sun. We will continue the weather cycle, drying out both sides. Let's repeat the rain cycle. Now the dry. We continue to repeat this process, representing the passage of many months. A great deal of soil has been washed away. Rocks are exposed and water runs off rather than soaking into the ground. The covered area has considerable underground water. The cleared area has very little. The plant roots draw some of the underground water up into the leaves. The water evaporates into the air. In this way, one large tree can return about 1,000 gallons of water per day to the atmosphere. The sun heats the surface of the earth and the moist air. The warm air rises, cools, the moisture condenses, and forms raindrops. Gravity returns the drops to the earth, and the cycle continues. When rain falls in our man-made desert, the water runs off into streams and rivers, carrying soil with it. Little water is stored beneath the ground. There is no vegetation to return the underground water to the atmosphere and continue the cycle. Does technology have an answer? We can irrigate and replace nutrients washed from the soil. By using a closed water cycle in this demonstration, we can observe what happens to the water when soil additives are used. There is a gradual buildup in the water of anything we continually add to the soil, such as fertilizers, DDT, and other insecticides. Even the mineral salts present in our underground water supply are building up. Eventually, the water supply itself becomes contaminated. The result can be an ugly wasteland, loss of food crops, loss of feed for domestic and wild animals, and loss of water for the development of cities and industry. In an area of 500,000 square miles between New Delhi and Karachi, India, man's misuse of land has created a wasteland, the Rajasthan Desert. In 1500 BC, this desert was an agricultural empire. However, the normal vegetation was weakened by the increasing demands of a growing population on this area. Deserts, in general, are regions where the air is subsiding. As the air sinks, it moves to a level of higher pressure, which compresses the air. When air is compressed, it warms, and its capacity to hold moisture increases. In the Rajasthan, with the loss of its grass cover, dust was carried by winds into the air. Dust in the atmosphere increases the subsidence of air. The presence of the dust inhibits rainfall. Since the source of dust is the desert itself, the cycle becomes self-sustaining. Without the knowledge of how to control the cycle, it remains a desert. When the winds blow, the property is anything but desirable. This desirable property is being mismanaged. Some changes are past due. There are about 34.3 billion acres of land on our Earth. Let's examine the 2.3 billion acres that make up the United States. 58% of the United States is used for crop and livestock production. 22% is ungrazed forest land. 12% is desert, swamp, or tundra. 5% is wildlife refuges and parks. 3% is taken up by our cities and towns. In the United States, we have altered the surface of over 60% of our land. In changing the land, we are changing the complex biological systems of the soil and the plants and the animals. Each year, about 700 square miles of land are consumed by expanding urban areas. What happens to the temperature of the surface land and the atmosphere when we replace vegetation with hard soil? The temperature of the cleared area is 24 degrees centigrade, 2 degrees lower than the vegetation area. The air temperature is 28 degrees centigrade over the cleared area, 2 degrees higher than over the vegetation area. The light meter indicates that the same amount of light is shining on both areas. Is the same amount of light reflected back from both areas? The light meter indicates that the cleared area reflects back much more light than the growth area. The reflective characteristics of the Earth's surface are called the Earth's albedo. These surface characteristics are a factor in determining the temperature and climate of a specific area. If we increase the albedo, the reflective characteristics, we tend to lower the surface temperature. Densely built up areas like cities reflect more heat energy back to the atmosphere, much more than forests or grass-covered fields which absorb the heat energy from the sun. Man-made deserts have high reflective characteristics. Highway systems may also increase the Earth's average surface albedo. If we calculate the difference between the amount of solar energy absorbed by the Earth and the amount reflected back into space, we find that in 1 year, 1 square meter of vegetation absorbs about 68 watts. 365 square meters would absorb enough energy to light one 68-watt light bulb year-round. Most of the absorbed energy is used to evaporate water, heat the atmosphere, and drive our weather system of winds and rain. Less than 1% of the energy is used in photosynthesis. This 1% is responsible for our food, fuels, and fibers. When we increase the albedo of the Earth's surface, less solar energy is absorbed, more is reflected back to space. A decrease of a few tenths of 1% in global radiation balance might produce a radical change of climate, perhaps another ice age. The net effect of all the man-made influences on climate is not known. Increased exhaust emissions may raise the Earth's surface temperature. Jet trails may lower it. Cities create islands of heat warmer than the surrounding countryside. Misuse of land can produce man-made deserts. Thoughtless use can produce man-made eyesores. Misuse of land is becoming one of the most serious and difficult challenges to environmental quality. A bay filled in remains filled. A virgin forest cut is gone. What price an inadequate sewage system? Land use is still not guided by any agreed-upon standards. It is instead the result of competing, overlapping government agencies and programs, private and public desires and prejudices, and economic incentives. This desirable property produces the food we eat, the oxygen we breathe, and the environment we hope to enjoy. It is a limited resource. We should manage it well.
Sorry about that. But it's not new information. Let's learn about glass from the old to the new through research. Circa 1950 something. Enjoy.
Industry today is shattering records for productivity. In all kinds of industry, as for example in glassmaking, immense quantities of raw materials are transformed into goods for the market. Here, raw materials are fed into a glass furnace. Processing these materials requires specially designed equipment and mass production techniques. Partly these develop out of ingenuity and chance, and partly out of experimentation. The results are products for the home, like the glassware being made here, and products for other aspects of modern living. Since a high rate of industrial productivity benefits everyone by providing better products at less cost, it is important for laymen as well as industrialists to understand what makes such production possible. Basic to this understanding is a knowledge of industrial organization. Each company is directed by a team of experts, the leaders of different specialized departments. Each department has a particular contribution to make to the work of the company it represents. For example, the production department relies upon men and machines to turn out finished products for the sales department to sell. In addition to production and sales, a purchasing department buys necessary raw materials, parts, and machines, and a financial department accounts for and finances all purchases. It also takes an engineering department to design and test equipment intended to increase the daily output of each worker and decrease drudgery. But newest of all the departments to gain a position of eminence in industry is research. Research is responsible for getting reliable answers to problems that affect the technology underlying production. Setting up experiments and intelligently interpreting the data revealed by these experiments is an important part of this research, which leads to improvements in old products, development of new products, and reduced costs for consumers. Industrial research concentrates on discovering facts that can be applied. Products of research are commonplace. They could be pictured in many different settings. But because of the universal use of glass products, the glass industry is selected as background for this story of progress. Glass in its many different forms provides one of the most versatile substances ever devised by man. In the home, it takes such different forms as windows, draperies, decorations, and tableware. One of the common forms is molded glass. Molding processes are used to make bottles and hundreds of varieties of glass containers to package goods for the market. Flat glass, window panes, and plate glass are forms known to everyone. Glass is made into corrugated panels, covers to protect delicate instruments, blocks for construction, acoustic tiles to deaden sound, picture tubes for television sets. Glass can be made into panels containing electrical resistance wires that radiate heat. Whatever the kind of glass, each is adapted to some special use. Some kinds are chiefly useful in the home. Others serve industry or the professions. The properties of each kind depend upon its ingredients. Glass through the ages and until 1880 usually consisted of sand, soda ash, and limestone. Mixtures that go into modern glass contain additional substances. Each is added to produce some special quality not attained by glass craftsmen of the past. Besides changes in mixtures, improvements have been made in the machines for making glass. Ingenuity and luck have helped develop some of the modern techniques and machines, but today it takes more than ingenuity and luck to satisfy man's increasing desires. For example, here's a tumbler. It looks perfect, but let's test it. One successful test that has been devised employs polarized light. Look for strains in the glass. They show up as dark areas. Undesirable strains could lead to early breakage. But when the tumblers are annealed by slow cooling, these strains disappear. This superior product is the result of experimental work. All systematic investigations of glass are relatively recent. Otto Schott, a German chemist, is often considered the first man ever to initiate a systematic program of research in glass. Schott's experiments were planned to improve the mixtures used to make lenses. About 1880, he began his work. He added different oxides to the customary formulas of sand, soda ash, potash, and lime. His work led to improved kinds of glass. Some of his glasses, together with others developed by his successors, make possible the high degree of perfection in modern optical equipment used to provide sharp visual images. During Schott's long life and through the intervening years, research has repeatedly demonstrated its importance. All of the fundamentally new uses for glass, as well as many of the improvements in the old, have resulted from research. Today, specialists in research continue to study the effects of new materials and procedures. Here is one such specialist. Like most of the younger technologists, he has a degree in science. His knowledge of glass developed in college. Like other students, he included field trips in his training. A special interest led him to make most of his trips to glass factories, such as a flat glass plant. This is where window glass is made. Raw materials are received by the carload. The sand, soda ash, lime, and other raw materials are measured into batches to be melted. Huge containers transport the mixtures to the furnaces. Periodically, a batch of raw materials is added to the other tons already being melted. A large furnace like this may hold several hundred tons at one time. Heat released by burning gas produces a temperature of about 2,700 degrees Fahrenheit. The heat transforms the mixture from its solid form into a molten, sticky mass. The molten glass moves from the furnace as a continuous ribbon. Knurled rolls maintain the proper thickness of this ribbon-like sheet. After passing through a cooling tunnel, the sheet is cut into sections. These sections, to be used in windows, are clearer and better than ever before. It's difficult to imagine how life would be without this product. Almost everyone has need for window glass. Plate glass, another important kind of flat glass, is made from special mixtures of raw materials. The materials are melted in a massive crucible. Once the melting temperature is reached, the batch is ready for pouring. The molten glass passes through rollers and forms a plate. Unfinished plates are sometimes called blanks. As soon as they have cooled, the blanks are ready for finishing. To simplify lifting and handling the large, heavy plates, glass makers use equipment fitted with specially designed suction cups. Finishing means grinding and polishing. These processes remove any roughness on the surfaces of the rolled plate. After the final polishing, the surfaces are so flat that each is almost a perfect plane. These plates are thicker than ordinary window glass and permit vision with very little distortion. Production methods for plate glass have been improved so greatly in this century that it is now available at relatively low cost. Much plate glass is used to make automobile windows. Containers such as bottles are another type of product in use for centuries. Of course, the glass makers of 100 years ago never saw containers like these. Making glass containers, such as bottles, is one of the most economically important branches of the entire industry. Bottles are made by blowing, as they were in the days of glass blowers. But the quality of glass bottles has been greatly improved, and the methods of production highly developed. Today, containers are not only better than ever before, but they are produced at rates that would astound glass makers of even half a century ago. Virtually every home or market in the world has use for some examples of the container industry's products. In some modern factories, glass blowers still practice their ancient art. No amount of systematic research or ingenuity has yet devised machines and procedures for making certain types of glassware. Glass blowers follow techniques handed down by generations of their predecessors. Precision and craftsmanship result from long years of experience. Here, a volumetric flask is being blown by using a blow mold. Glass blowers make equipment like this flask for the laboratories of science. But like any hand operation, their output is limited. Wherever possible, machine production replaces this colorful art. Much of the laboratory wear of today is made by modern high-speed mechanical means. Even tools like these are changed as experiments reveal ways of doing the work more efficiently. Marking products like graduated cylinders requires precision machinery. The manufacturers of laboratory ware continually search for improvements, such as glassware with greater resistance to shock, new mixtures of raw materials, improved manufacturing procedures, and refinements in testing apparatus contribute to more perfect products. Most glass products have benefited from research, but some are direct results of research, such as glass blocks. Crude blocks of glass were made as far back as the days of early Rome, but such early counterparts could not compare with the quality of glass blocks today. Mass production of modern blocks is the outcome of a systematic research program begun in the early 1930s. The program was planned to perfect mixtures and develop procedures for high-speed, efficient production of blocks with unique properties. Glass blocks have opened up new uses for glass and helped make glass competitive with some of the other common construction materials. This competition favors the consumer because it offers him a greater variety of materials to select from and leads to lowered prices. It's an example of more and better products for less money, an important contribution to a high standard of living. Glass fibers, like glass blocks, have been known for centuries, but were merely curiosities until recently. To make fibers, the melted glass is formed into marbles. After inspection, the marbles are conveyed into an electric furnace. Each marble will make more than 100 miles of fibers. Fibers can be made from these marbles that are much finer than a human hair. Transformation into fibers for textiles depends upon molten glass flowing through fine holes in a platinum trough. Textiles like this drapery can be manufactured from fibers of glass. Such textiles resist many of the hazards that could destroy ordinary fabrics. The raw materials of glass can be made into other kinds of fiber products without going through a marble stage. This is glass wool. Fibers of glass wool have many valuable properties. These fibers will neither shrink nor stretch, and they will not burn, rot, or rust. The fibers can be sandwiched between layers of heavy paper to form blankets like these. Each blanket provides insulation that will block or reduce the transfer of heat. It can provide insulation for a building to help keep the interior cooler in summer and warmer in winter. To insulate buildings, the paper-covered blankets are tacked between wall or roof supports. Compressed more firmly and treated with a special binding material, glass fibers are made into a pre-formed kind of insulating board for such uses as roof and cold storage container insulation. Other types of fiber wool bats are used as insulation in appliances designed either to exclude or retain heat. Treated in other ways, fibers of glass can be made into insulation that deadens sound from automobile or aircraft engines. retainer mats and separators for storage batteries, pre-formed coverings for pipes, and filters for air conditioning and forced warm air heating systems. And here is a special use. This is a bulletproof vest which contains for its armor plastic sheets reinforced with glass fibers. Vests like this have saved many fighting men from vital injury in combat. In these and other ways, research helps lead from the old to the new in glass by developing better products for modern living. The practical value of research in glass is demonstrated in many settings. For example, improved optical glass has meant improved spectacles, and improved spectacles mean greater enjoyment while reading, driving, or using our eyes in other ways. Optical glass makes possible the fine lenses of cameras. More perfect lenses for microscopes contribute to the development of virtually all the sciences. The microscope reveals objects too small to be seen by the eye alone, such as this reproductive action of a one-celled animal. Nearly all aspects of biology have profited by the use of optical glass. There is always the challenge of problems yet unsolved. For example, who will discover a cheap method of extracting aluminum from clay? An ordinary clay brick contains about a half a pound of aluminum, but no one knows how to extract it economically. Or who will learn to harness the power of the waves, extract more of the valuable elements in seawater, or use energy directly from the sun? Who will be first to conquer outer space? Who will be the next to convert some glass mixture into a new and unique product for the market? Progress in glass, as in industry generally, becomes increasingly dependent upon research. The results of systematic experimentation may not often be as spectacular as in this production of electric lamp bulbs, but inevitably, research leads to more products at less cost to serve the needs of more people. Industry is learning to use research effectively and is thereby helping raise our standard of living. Today, men and women are working to solve many different problems. Their success will influence our future. The achievements being made in glass and in all other industries assure for industrial research a role of increasing importance in furthering industrial progress and the welfare of our society.
Glass for the future! Glass! That's pretty great. Beautiful assembly line footage in there. So again, I have a film set up on the scanner. What is it next? It's boiling point and pressure. Enjoy.
Everyone has run low on gas before. Most likely you've had to gas up a car at least once. Gasoline is a part of our everyday lives. And what goes into making gasoline is a part of physical science and you. Let's talk about boiling point and pressure and how the manufacturers of gasoline are concerned with it every day. This is one definition of boiling point and pressure. Boiling point is the temperature at which the vapor pressure of a liquid is equal to the pressure of the atmosphere on the liquid. Vapor pressure is related to the amount of kinetic energy within the liquid molecules. Before we find out why people who make gasoline would be concerned with boiling point and pressure, let's take a look at an experiment showing how pressure affects the temperature at which water boils. Water boils at 100 degrees Celsius at sea level. You can see our barometer reads 29.9 inches of mercury, and the water is boiling at 100 degrees Celsius. Let's look at a model of the water being heated. The blower represents the heat being applied to the water. The moving particles represent steam, and the two red balls represent air at atmospheric pressure. As we turn up the blower, it represents a rise in temperature, which increases the evaporation rate. The steam detector measures the evaporation rate. The meter moves erratically between 20 and 30. This will represent the boiling point of water at atmospheric pressure. We will mark that point, which will calibrate our device, and we'll label it 100 degrees Celsius. Now let's go back to the real boiling water. We're going to reduce the atmosphere over the surface of the boiling water by removing the air with a vacuum pump. All of the water vapor coming off the pot is trapped in a chemical that absorbs water. The meter readings on the pot indicate that we have reduced the atmospheric pressure by 5 inches of mercury. The temperature of the boiling water is now 95 degrees Celsius. Back at our model, notice that one red ball is in position over the water, symbolizing the reduced atmospheric pressure due to the vacuum pump. The blower frequency is adjusted so the meter readings are again between 20 and 30. Note the position of the dial is at a lower setting representing the lower temperature required for boiling. Let's see what happens if we increase the atmospheric pressure over the boiling water. First, we'll remove the vacuum pump and replace it with a small glass nozzle. The nozzle restricts the immediate release of the steam over the liquid. This tends to raise the pressure of the vapor over the liquid in a quasi-confined space. The boiling point is now 105 degrees Celsius. In our model, we now have 3 red balls over the water to symbolize the increase in atmospheric pressure caused by the glass nozzle. We again adjust the blower to the same readings between 20 and 30. But this time we have to increase the dial setting, which represents the higher temperature required for the water to boil. The pressure at 105 degrees Celsius can be estimated at 35 inches of mercury. Now, let's relate these experiments to gasoline. Gasoline is refined from crude oil, which is recovered from oil-bearing formations beneath the Earth's surface. The crude oil is distilled and chemically modified to yield a large number of products. Distillation of crude oil is accomplished in a tall device called a fractionating tower. The crude oil is vaporized by heating in the furnace. The heated oil is pumped into the fractionating tower. Once there, portions of the crude oil vapor form liquids which collect on trays in the tower. The hydrocarbons in the oil that are most volatile or have the lowest boiling point go farthest up the tower before condensing to form liquids. The trays upon which the liquids condense are arranged so that the heated vapors bubble up through the liquid in the trays. This gives an efficient separation of the crude oil into fractions based upon the temperatures at which the hydrocarbons boil. The refined products are pumped into large tanks as either a final product or stored for further refining. Let's see some more examples of things concerned with boiling point. This dry cleaning machine depends on distillation to reclaim and clean the expensive dry cleaning fluid so it can be used over again. The dirty fluid is heated to its boiling point. This turns it into a gas which is condensed back into a liquid and stored. When all of the fluid has been boiled away, The only thing left in the boiler is the dirt and soot that the fluid absorbed. The household pressure cooker also utilizes boiling point and pressure. As the evaporating vapor builds up under the lid of the pressure cooker, pressure upon the surface of the liquid is increased, which prevents boiling. This raises the boiling point of the water. The increased temperature of the boiling water cooks the food faster. Conversely, if the pressure over the water is reduced, the temperature at which boiling takes place is reduced.
What do you think would happen if pressure is reduced to the point of a vacuum? This causes special problems for the United States space program.
The NASA astronauts must use special spacesuits to protect themselves from the extremely hostile environment they work in. Space is a vacuum, and our experiments showed how less pressure means less heat is required for boiling. So liquids would boil instantly in outer space. The external pressure is so low that a liquid propellant, battery fluid, or human body fluid exposed to it would boil. Without the suit, the astronaut's blood would boil instantly. Boiling is actually evaporation taking place beneath the surface of a liquid. It forms bubbles of gas which are buoyed to the surface where they escape. The speed of the molecules forming gas must be great enough to exert as much pressure within the bubble as the atmosphere and water above exert. Therefore, boiling depends not only on temperature, but on pressure as well. More surface pressure means more heat will be required to boil. Less surface pressure means less heat will be required to boil. Let's take a look at our experiment again. Energy must be supplied for boiling to continue. This energy is absorbed by the liquid as it becomes a vapor. The energy promotes the conversion of molecules from the liquid to the gas phase. Spacing between the gas molecules is greater than that between water molecules. Here we reduce the atmosphere over the surface of the boiling water. Notice that one red ball is in position over the water, symbolizing the reduced atmospheric pressure. Now we increase the atmospheric pressure over the boiling water. Three red balls symbolize the increase in atmospheric pressure. The boiling point of glycerol is 290 degrees centigrade at standard atmospheric pressure of 29.9 inches of mercury. If we boiled this liquid in the same experiment instead of water, the temperatures would be different, but the results would be similar. Remember, crude oil is made up of many different chemical parts. Each of these parts has a different boiling point. During fractional distillation, how does the temperature vary as the crude oil travels up the tower?
Let's review that definition again.
Boiling point is the temperature at which the vapor pressure of a liquid is equal to the pressure of the atmosphere on the liquid.
After seeing the examples and how they relate to boiling point and pressure, the definition seems to make more sense now. So the next time you fill up with gas, think about how boiling point and pressure affect us. We're exposed to physical science laws every day and don't realize it. Try to see what these laws mean to us as we introduce you to the physical sciences.
A little dry. Let's, how about some fire, Scarecrow?
Say, what makes fires? Huh? What makes fires? Wait here. Matches. Matches make fire. Oh, wait here. Cigarette lighters make fires. Wow. But I don't want a fire to start. Then leave these alone. Don't play with matches. Stay away from these. Okay. But what if a fire just starts? By accident or something. If a fire starts, you leave. Get out of the house quickly. Look down there.
Annie!
Yeah?
Hey, Annie, I know all about fire. I learned it in school.
That's good.
Hey, I'll be right down. Hey, Annie, guess what I learned in school? All about fires. And now that I know, I can tell you.
That's nice.
So I'm going to tell you. Now listen. This is it. Now suppose you smell smoke in the house. You smell smoke.
Right, you smell smoke.
Well, then guess what you have to do?
Well, what do?
Well, first you got to look all around. See where the smoke's coming from. You understand?
Yeah.
Maybe it's coming from that door over there.
The kitchen? Nah.
Sure, it could be. Then you go carefully over to the door and feel it.
Feel the door?
Yeah, you feel it to see if it's hot. If it's hot, don't open it.
Oh, all right. Well, if it's not hot, what do?
Well, then you can open it. But just a bit, just an inch, you can open it and see what's inside.
Oh, okay.
See, if you see fire, you got to close it. Oh, I see fire. There. So you got to close it. Do you understand?
Okay, you close it. Then what?
Well, then you got to find another way out. Maybe a window. Or another door.
Yeah, that figures. You'd probably go out that door.
Yeah, come on, let's go. You got to come too, you know.
Oh, for heaven's sake. All right, I'll come.
Come on, let's go. But wait. Suppose there's a lot of smoke.
You get a lot of coffee.
Listen. Heat and smoke rise up. Cool, fresh air is down near the floor. So you get down and you crawl out.
I crawl out?
Yeah, it's not hard. Come on, try. We'll just crawl out like this. See? That's not...
Wait a minute, I forgot my book.
No! You can't go after anything. You gotta just get out as fast as you can. Come on now. Come on.
Oh, for heaven's sake.
See that you gotta get out.
All right, so I crawled out the door. Then what? Well, then you got to go find someone and tell them to call the fire department. You got to tell them your name and where you live, and you tell them that there's a fire down here, right? Yeah, that's it. Can you remember? Sure, I can remember. Come on down now. All right, I'll be right down. Yeah, come on down. Okay, that's all I've got to tell you. Good. I'm going to read my book. Okay. I'm going to play. Okay. Hey, hey, I smell smoke. Oh, yeah, we played that already. No, but I really smell smoke. I really do. Well, if you really, maybe there's a real fire. Fire? Oh, my gosh! What am I going to do if there's a real fire? Well, we do what you said. First, we got to look to see where it's coming from. Hey, it's over here. I'm going to go over. Don't open it. Okay. I'm just going to touch it. Right. Yikes! It's hot! It's hot! Then don't open it. We'll find another way out. Right. Up this way? We'll have to go out the kitchen door. Okay. No, wait. Remember that there's going to be cool air down here. So come on down. We're going to crawl out. Oh, that's right. Hey, wait a minute. I left my truck over there. No. Don't go back for anything. That's what you said. Come on, get down, and we'll crawl out as fast as we can. Come on. Okay. Hey, now we're out.
What happened?
What, may I ask, is a dear little cupcake like you doing with nasty old school books? My dear child, we haven't had school or books in ages.
No school? Really?
Why don't you get rid of that school book? You can drop them in here.
It'll get all burned up in there.
Well, of course it will, dear child. And so it should. Books tamper with man's basic, natural ignorance. Now, what could be worse than that?
But I can't burn this book. It's school property.
Nonsense! Apple sugar. You just need to get into the mood.
Books are not where it's at, teaching you how to spell cat. I know you'd rather play, so why don't you throw all your books away? Books are made for burning, the fire is already yearning to put an end to any learning.
1, 3, 5, 9, throw them in the fire's fine.
Put the books in the fire, see the flames growing higher. Burning books is our heart's desire.
2, 4, 6, 8, time to incinerate.
Books will not make you wise, and reading's bad for your eyes. I am sure you agree, so why don't you give all your books to me? Books are made for burning, fire is already yearning to put an end to any learning.
This one here is very good about a man named Robin Hood.
Put the books in the fire, see the flames growing higher. Burning books is our heart's desire.
No, I never liked Tom Sawyer. I won't be a book destroyer.
Books can only confuse, teaching you things you can't use. You should listen to me. Burning your books will set your mind free.
Books are made for burning, fire is already yearning to put an end to any learning.
stop. Yeah, we don't know what happened to those crocheted puppets who were caught in the midst of a blaze. I might have another copy of the film. I don't know. I have to look and see. Like, yeah, I'm kind of wondering what happened. But it's possible that they are ash in a pile of melted synthetic yarn. It's totally possible. That last thing, of course, was from Magnificent Major, which is something that we show whenever we watch a film about books, reading, fires, or when I just feel like I want to see some awesome disco from the 70s featuring Tisha Campbell. It always makes me feel good. And inadvertently, I showed a bunch of stuff about fire, pressure, manufacturing. That was not intentional. It's just kind of what kind of popped up. So there you go. That's the way it is here at AV Geeks. Thanks for tuning in. Very much appreciate your comments. Please hit the thumbs up button. Even if you've done it recently, it's a great way to tell the YouTube overlords who now have an installed device in my house to keep an eye on me. Doing the thumbs up or the subscribe, make sure that this does not turn on me and take my life at some point. You can also donate via ko-fi.com/avgeeks. Give us some coffee, or patreon.com/avgeeks, and that allows us to buy books like Puffin Stuff and other stuff. I'm doing research for the upcoming Saturday Morning Dinah Show, which features Croft Superstar or Croft shows, and we're recording Lidsville, but I don't know when it's going to air. But Lidsville is an outrageous show with hidden drug implications, perhaps. I don't know. Anyways, thanks for tuning in, and we'll be back again tomorrow. What is tomorrow? Thursday? Holy cow. Just burning through this week. Anyways, we'll see you soon. Everybody take care. Bye.